Oh, thanks, Arthur. Well, this is great because I think Arthur and Jeanette and Peo have done a really excellent presentation of actually some of the content of the ontologies that have been involved in the digital twin project. And then later on, we'll hear even more detail from De Hong in terms of the actual ontologies. So what I wanted to maybe emphasize a little bit more in my talk right now is, oh, why is this? Why this is okay. Sorry about that. This bar is sitting in front of me here. Is that distracting people? Can people see that? Okay.
Oh, there you go.
Um,
I
okay.
think we're fine.
Okay. So what I wanted to focus on is more of the kind of underlying methodology that we want to use in tackling the kinds of problems we're encountering with the digital twin. So ultimately, we can kind of think of this as, asking natural language questions about data sets. So just say a simple, trivial data set here. Alice supervises Math 456, which is a financial project, and Bob supervises MAE 123, which is an engineering project. And we want to know, well, is Alice a manager in the division, or is Bob assigned to any projects? From the data alone, we can't answer these questions because there's nothing in here about what a manager is or what it means for someone to be assigned to any particular kind of project. Right. What we do is we use what we do is we use background knowledge for these relationships that are implicit in the data. And then that background knowledge together with the data is how we answer these questions. So in order to answer those earlier two questions, we have to understand, what do supervises, assigned to, manager, what do these concepts mean? And then how do we represent this meaning and use it to answer the questions? So the idea is an ontology is a way of declaring both the terminology that we use in our representation, together with some way of specifying the meaning or the semantics of these terms within a formal logic. And another example I like to use, maybe it's a little more kind of financial and less trivial, would be, what are the households in a particular postal code that have a household debt over $500,000? So you're not going to be able to answer that question simply by doing a retrieval query, right? Because you have to understand, first of all, what is household debt, right? So there are various kinds of debt. There are mortgages, there are lines of credit, there are credit cards, there are personal loans. And you need to be able to understand that these are different kinds of debt. And so what you would do is need to retrieve all those different kinds of debt and then sum those together. But then you also have to understand, well, what is a household? Right? So there are different individuals who live at the same address that constitute a household. But what exactly is the definition of household that you would be using? And it's very important because, for example, you may have two spouses that would be having this names on the same mortgage, although they could have individual credit cards. And so when you're actually combining that household debt, you would perhaps combine the separate credit card debt for each spouse, but you would not add the mortgage debt for each spouse because those two spouses together have that mortgage as their combined debt. So the way you would add the various kinds of debt together, again, depends on the semantics of household and debt. So the idea is that we have ontologies that can allow us to do this. And within this project, as Jeanette and Peo have kind of illustrated, is that we have a whole set of ontologies that we used in order to answer the competency questions for the digital twin. However, right, so this is kind of one of the challenges here is that manually designing and evaluating an ontology is very, very resource intensive, often requiring like hundreds of work hours. The kinship ontology that Jeanette mentioned, took several experts, 6 months in order to really design. And you can say, well, like everybody has, there's always some kind of kinship ontology on the web. There's family history, knowledge base, FHKB. The problem is that it's not only the design, it's not just producing the axioms of the ontology, but testing it out to determine and evaluate whether or not it is complete enough in order to answer the competency questions that you have. And just like in software, coding is actually a small part of a software project. A lot of the life cycle of a software project is in the testing and maintenance of the software. We see something very similar with ontologies. That when I'm talking about resource intensive, often it's not just the design, the production of the axioms, but it's also the evaluation that takes time. And then the other thing is that even if you have the ontology, so in this particular case, right, we had a variety of ontologies, the suite ontology, the different kinds of soil ontologies, time, as Peo nicely illustrated. We have the problem then of integrating that with enterprise data. And the problem, and then also then using multiple ontologies requires this additional mappings. And right now, again, the technology is manually specifying these. So even once we have the ontologies, we have these other two tasks of integrating with data and integrating multiple ontologies that in the worst case scenario can be just as difficult as designing the ontologies from scratch. So we have this big resource intensive design process that is currently sort of, I think, a bottleneck in terms of applying ontologies. And so the idea that we have is rather than manually designing an ontology first, and then afterwards associating with data, is there some way that we can semi-automatically design the ontology from the data itself? And so this effort we were calling CDO, an acronym for Semi-Automated Design of Ontologies. And the idea is that we will be generating modular ontologies through kind of three different techniques. We'll see on the next slide. Starting off from data models, using natural language, and then learning from examples. And I mentioned this word here, modular ontologies. The idea that you can take a very large ontology and only use those aspects, those subtheories that are necessary in order to solve the COMPSI question, to do the reasoning. So one example is FIBO, the Financial Industry Business Ontology, which is a very, very large ontology, and it is not has not been modularized. So if you say, okay, I only want that part of FIBO that I would need in order to answer questions, like I said about the, what are the households in a particular postal code that have, again, a household debt over some amount. In order to understand debt, I want to say, well, can I just get that part of FIBO that worries about debt, that axiomatizes debt? I don't care about other concepts within FIBO. You can't get that, right? You have to take the entire ontology, which is almost too large for a lot of the existing ontology software to really manipulate. So, and the other thing too is you say, well, we could modularize it. But again, the problem of modularizing a large ontology such as FIBO, or in the context of what we've seen earlier today, the suite ontology, again, also a very large ontology that is not modular. The effort to modularize the ontology after the fact can be just as difficult as designing it all over again. So we want to be able to design ontologies that are modular by design, not just modularizing after the fact. So you see here the architecture we have for CDO. And the idea, again, is to start off with the kind of the artifacts that are already there and use those as ways of building the ontology. So this is a very data-driven ontology, right? So another kind of drawback of a lot of ontology research or ontology deliverables is that these ontologies get designed sort of in a bit of a vacuum. And again, the problem is mapping it to this concrete data that you have. We want to start with that data and design the ontologies that can answer the COMPSI questions that we've already kind of seen presented earlier today. So we start off from three basic sort of places. One is on the upper left here, we have data models. So we'll very often an enterprise has their data models, UML class diagrams, entity relationship diagrams, and those contain implicit semantics. And so we want to extract the ontology that's implicit in the data models. There's also a wide variety of natural language documentation that either supplements the data model or is completely external to the data model, various kinds of concepts that people could not represent in the data model, and we want to be able to leverage those concepts. And then finally, there's actual data sets themselves. So in the context of the POC we've been looking at earlier today, these would be climate data, location data, kinship data. So you have actual data sets that have all of these things. And even the climate data right? There'd be precipitation, there'd be temperature. As Arthur mentioned, there's a sort of a spatiotemporal aspect to a lot of the data. But we want to be able to say, no, start with the data itself, because the intended semantics of the data is what we actually are going to be reasoning with. And then we combine all these together in what we call the Hashemi procedure, named after one of my earlier grad students who proposed this procedure, which effectively is how we would be learning the ontology using a repository. And so this is sort of the outline of what I'll be talking about in the remainder of my talk. So first of all, the data models. So the idea is to think of the data models as seeds for ontologies. They provide the classes and relations that provide what we call the signature of the ontology. Data models also contain constraints that are implicit in the semantics of, say, something like a UML class diagram, and we can formalize those, automatically formalize those within the axioms of the ontology. So an example data model here, again, we have managers supervise projects, which are assigned to employees. There are various kinds of managers, coordinators, directors. There are subclasses of projects, engineering and financial, and there are different kinds of employees. Say an engineer is a subclass of employee. So what we do is we could extract from that the different classes, become class relations within the ontology, and supervises and assigned to are the associations you see in this data model, and those become binary relations. And again, also there is implicit semantics within the structure of that data model, and we can automatically generate these kinds of axioms. So this is an example of first order logic, and we've implemented software that can take any data model. The implementation works for Irwin. We can also extend it to UML class diagrams, and it automatically generates then the axioms associated with that data model. So again, this provides now sort of a first draft, if you will, of the ontologies, and it conforms. We can again formally prove that it conforms to the intended semantics of the data models that are already present within the enterprise. The second component of CDO was going from natural language. So here we had the natural language documentation, and the procedure that we use here to extract axioms is known as semantic parsing. So semantic parsing is the task of converting any kind of natural language statement into some logical form. There have been efforts in the past, say, generating SQL queries. If you kind of look at the innards of Alexa, there is what's called an abstract meaning representation within Alexa. And so they, of course, implement a parser that translates natural language statements into that representation, so then they can do reasoning. Arthur earlier mentioned Prolog. What we were looking at is generating first order logic. And so we actually look at kind of a restricted form of semantic parsing. I mean, the general problem of semantic parsing, you also need to be able to recognize which ontologies are going to be needed. So for example, the word part can have part of, you might think, okay, that's a very simple relation, but it turns out there's probably about more than six different kinds of parthood ontologies that you might be thinking of when you use the word part of. And so you'd want to be able to identify, well, which part of are they referring to here? That's the more general problem of semantic parsing. In this particular case, we have a more restricted problem because we're kind of leveraging this data model or these existing data models, or also we're leveraging existing data sets. We kind of know the signature of the ontology, so we're kind of focusing on that. And we're also not looking at process data within this POC. We look more at what are called stative verbs, verbs that are representing a relationship, like Alice supervises a project. We're not representing the activity of supervision. We're representing that relationship between Alice and that particular project. So this allows us to do something called phrase mapping that associates classes and relations to the signature, and we can then generate axioms. And a demo video of this is also available. Okay, so that's sort of the two parts there. And in a sense, these two parts are not maybe particularly innovative in the sense that, I mean, people are doing semantic parsing. People have done work in the past of generating logical expressions from data models. But what we really wanted to be able to do was to then take these and to learn an ontology, particularly learning the ontology directly from examples and counterexamples. the idea being that ontologies are designed with respect to a set of requirements. Designed with respect to, say, functional requirements. Ontologies have semantic requirements. And there are various ways, but the primary one using in our research lab and in this particular Flamel project was this idea of competency questions. And again, the idea of a competency question is that this is a query that is playing, say, I guess, roles at two different parts of the ontology lifecycle. At the beginning, it's identifying, what's the scope of this ontology? What are the fundamental kinds of relationships, the classes of things, the fundamental relations that we're going to be looking at? And then towards the later in the life cycle, it's serving as a way of identifying, is the ontology that we've designed to this point complete enough? Again, is it sufficient for us to answer the questions? And as I illustrated from the very first slide, the idea is we want to be able to have data together with a background knowledge. And that background knowledge is the ontology, and the competency questions are then serving as a way of saying, once we answer this question, we are complete enough that the ontology is ready for deployment. The idea is that these requirements are sort of scoping out what we call the intended interpretation. So the meaning, what do we really mean by a particular kind of concept? I said earlier, say the household debt, and you want to be able to exclude various kinds of unintended interpretations, ones that don't match that particular meaning. The idea is that the data sets themselves really provide this intended semantics, this intended meaning. And you can kind of think of it in two ways. I mean, one is that, say, clean data sets that don't have any semantic errors. Those should be consistent with the ontology. Again, the idea being if there are no semantic errors, they should be consistent with the intended meaning of the terms that are being used. And so these serve then as the kind of the intended models or examples for the ontology. Conversely, data sets that have quality problems, that have perhaps kind of inconsistencies, will be ones that should make the axioms of the ontology false. So these serve as counterexamples. So you can kind of think of various sort of examples that a particular you can be located in two different places at the same time, or two different objects can be located in the same place at the same time. You would identify these as being specific kinds of quality problems within your data. And again, that would serve then these kinds of data sets that have these quality problems would serve as counterexamples. So whatever ontology you come up with should be inconsistent with them. So then the idea of this ontology learning procedure, again, we were calling the Hashemi procedure, is that given a set of examples, which are representing the intended models, and a set of counterexamples, which should be inconsistent, we want to search through an ontology repository to find the best match. So an ontology that matches all the examples and none of the counterexamples. And when we're talking about learning here, we're not talking about, say the machine learning efforts that are in vogue right now, large language models, et cetera, which require an enormous amount of data in order to learn. What we want to be able to do is learn from a handful of examples and counterexamples. Right. So we don't have the luxury of having a lot of different kinds of carefully curated data. We want to be able to learn this ontology from just, again, a handful of examples. So the idea is we have kind of two phases here. One is this discovery phase where we are searching through a repository to find this best match. But then it might, given the examples you have, they might not be sufficient to actually identify a unique ontology, that there may be more than one potential match, or even there might be a potential match, but we're considering this to be kind of a hypothesis that it actually works. So there's a second dialogue phase where a user can interact with the system. And so the idea would be once the system finds a potential match, it generates some examples and counterexamples, give them back to the user for them to classify. And so if the user then agrees that, yep, all these models you generated are correct, and all these counterexamples you generated, those are also correct, we say we've had the right ontology. If the user disagrees, then we refine the search. In a worst case scenario here, if we can't find an exact match, even after this dialogue phase, then at this point, we would need to bring in a kind of an ontology designer to really kind of see, okay, manually figure out what's going on here. Now, for this work, we use the Colore, the Common Logic Ontology Repository, which is a project that we host here at the University of Toronto in the Semantic Technologies Lab. It uses Common Logic, which is an ISO standard, as a kind of a test bed for doing this kind of ontology research. Now, you might kind of ask, well, wait a sec here. Since we're designing new ontologies, how can you possibly use a repository? I mean, the very fact that it's a new ontology means that it shouldn't actually exist, because if it existed, we could simply reuse what's out there. We don't even have to design a new ontology. But in fact, this is a new ontology. So how do we sort of resolve this particular sort of paradox? The idea is that we're actually not, the repository is not contain, in our example here, does not contain an existing, say, digital twin ontology that stitches all those together. Effectively, what we have is that within Colore, we have a wide variety of ontology patterns, which effectively are different kinds of mathematical theories, theories of orderings, theories of graphs, various algebraic structures, and other ways of combining these things together. Other patterns are generalizations of geometry. So in fact, that earlier data model that I showed about managers supervising projects, that actually has the same underlying structure, right? It matches the same ontology pattern that we find in what are called incident structures, which again are a generalization of geometry. So the idea is that we're not searching through domain ontologies, for example, location ontologies, geospatial ones, or these other sorts of specific domains, like say soil ontology, for example, is one that we'll hear later on. So we don't have a repository of soil ontologies or environmental ontologies. The repository is a collection of these ontology patterns, and that's actually what we're searching for. And the idea is that we have effectively a mapping. So for example, project manager supervises, I mentioned that it corresponds to this generalization of geometry. And in this, to kind of identify, say, well, okay, which patterns are we looking for? You could say, well, projects behave as points in the geometry, managers behave as lines, and the supervisor's relation is this relationship between lines and points. And by using these mappings, what we call translation definitions, this is then what allows us to say, okay, our data is in the signature of projects, managers, and supervisors, but using these mappings, we're actually searching through the space of these geometry ontology patterns. And that's how we will then match up with the data in terms of the examples and counterexamples. So the Hashemi procedure would say, okay, I found this particular kind of mathematical theory that matches all the examples of your data and none of the counterexamples. And then it translates it back into the signature of project manager and supervisors, gives that back to the user. And then also the axioms would similarly be translated. So the axioms won't be talking about points, lines, and et cetera. And they'll be talking about projects, managers, and supervisors. So the ontology gets translated back into the signature of the user. So in terms of some future work here, right now, we kind of assume that we have the right we've identified the right kind of hierarchy within Colore. Like, are we talking about ordering? So which pattern are we looking for? We also have to figure out the more general problem of identifying how do we search through the different mathematical theories or different classes of mathematical theories. The other thing is the initial pilot, we were kind of designing ontologies that had no modular structure, so they're very small. And we're currently finishing up the implementation where we actually do the explicit modularization as we are going along. So we're using this kinship ontology that has been alluded to in 2 earlier presentations, where we have one module related to the ancestor relation. We have one module related to the spouse relation, and the ontology itself is a combination of those two. And so we are generalizing the procedure, almost have the implementation done, to actually recognize and design that modularization explicitly. So then in summary, right, we have this kind of innovative architecture for the semi-automated ontology design. We have a tool that can generate axioms from logical data models if they're present. We have a natural language tool that can identify interesting natural language statements within documentation and then translate those into axioms. And then those are then fed into the Hashemi procedure, which can take the data and identify the mathematical theories that are patterns and then provide the ontologies. So that's sort of a gist of the methodology that we have utilized in designing ontologies. DeHong later on will give more insight into the actual ontologies that we use in FOML, as Janesh showed on an earlier slide, and that was implemented in the knowledge graph. So I just want to end early there in case there were a few questions.